Hi, I am Ridon Gu from Minnesota State University. I'm here to present our work, a loop-aware Autotuner for high-precision floating point applications. Let's start with the introduction. Floating point computations play a really important role in various domains, like molecular dynamics, climate modeling. However, one of the biggest challenges in floating point computations is the reproducibility issue. This is because of the approximate nature of the floating point arithmetic. The first error is generated when you do the computation. You cannot keep unlimited length of the results. You have to rounding the results to within the range of the floating point representation. The second error is called truncation errors. There are some equations like Taylor series for trigonometric functions. They have unlimited length. So you have to truncate the equation also within the bit representation of the floating point arithmetic. With these two kinds of error, the associative arithmetic like addition and multiplication are not associative in the floating point domain. For example, if you add a set of values in different orders, you may not get exactly the same results. And also in those molecular dynamics applications, the repeated accumulation pattern like a summation or repeated multiplication are pretty common. So in this case, those errors will generate a big errors. To solve these problems, the existing approaches, the first one definitely is high-precision libraries. They can provide better accuracy compared with standard floating point representation. However, they come with a really significant cost. For computational fluid dynamic code with 256-bit representation, it is around 80 times slower than the standard double precision. To solve this problem, the mixed precision tuning becomes more and more popular in CPU domains. Those works mainly do the mixed precision among the standard precision, and they can provide better accuracy compared with low precision like single precision, and also they can have lower time cost compared with the pure high precision representation. And also there are some other tools like interval arithmetic tools and also the verification tool. They also work on the standard precision for your floating point programs. The interval arithmetic tools is trying to give you an accurate error band based on a given range of the input. And also the verification tools can let you to better understand your floating point results across different platforms and also different compiler flags. With those in mind, let's look at what's the mixed precision tools on the CPU domain. So the parsimonious is a state-of-art tool that trying to lower the precision of a set of variables based on data search, and also combined with blame analysis and also some machine learning techniques that can try to reduce the search space. And the next tool is called Autotuner. They are trying to give out a rigorous error band based on the mathematical deduction and also solver. And also latest work called Autotuner. They are trying to use dependencies identification to reduce the search space to tune a group of variables of floating point programs. However, also has some challenges. First one, they don't support high precision. Second, they have a very gigantic standard search space. Although they already use some techniques to reduce search space, however, all of them are they work on the small programs in terms of number of variables. Third, the lack of the robustness to different inputs. Although all of these works support to do analysis on the variable inside the loop, however, none of them considers the frequent execution of the loop. Basically, they treat all the variables, no matter if they are inside loop or outside loop, the same. So once you change the data input size, you have to rerun the tuning using their tools. Next one is the lack of consideration for error propagation. as we mentioned, for those repeated accumulation pattern like global summation or repeated multiplication, they have a huge impact on both performance and accuracy. Last, except for the blend analysis, none of them use a command analysis for the computational patterns that can largely reduce the search space. Okay, with those in mind, we have designed our own Autotuner tools on CPU. The goal is first is trying to provide a tuning strategy that have limited search space that are possible to use on those HPC applications. And also we want to have a robust tuning strategy to different input variability using the loop analysis. And also we consider error propagation from those repeated accumulation pattern like global summation through leveraging combined analysis based on loops and data dependencies. Second, we want to address the mixed precision tuning between standard and high precision. Next, we also provide insights on those accuracy and performance trade-offs on CPU platform, and also implement a compiler-based auto-tuning tool that saves the effort from user. Then let's look at some background. The floating point standard 754 defines the floating point format with sign, exponent, and mantissa. The mantissa has fixed size for different precision that limited the bit for results. So this creates the numerical errors we have mentioned. Then it will have the reproducibility issue and also the big errors from this repeated accumulation. To solve these problems, the high precision library uses dynamic size for high precision arithmetic. There are two categories of that. The first category is called arbitrary precision. Just like the right-hand figure, the extended mantissa and exponent strictly follow the attribute standard, so they can provide a way better accuracy compared with standard precision. However, they come with a significant cost we have mentioned before. The second category is called composite precision, like a right-hand figure. They use multiple standard precision to represent a single high precision value. For example, this Canterbury composite precision library can use 4 double precision to represent a 256-bit high precision value and achieve around 10 minus power of minus 60 to 10 power of minus 30 error rate compared with arbitrary precision library, which has lower accuracy, however, is already enough, have way better accuracy compared with standard precision. And the best things of composite precision is the way better performance compared with the arbitrary precision. We can see it from our experimental analysis. Okay, let's look at the details of our design. The first is what's the candidate precision choice, and why do we choose the mixed precision between standard and high precision? The first reason definitely is the accuracy demands of those scientific applications, like we mentioned. The repeated accumulation pattern is very common in molecular dynamics applications and other domains, which can have a very big errors if you're adding up a large amount of values. Second, the performance gap between standard and high precision are way larger than those gaps among the standard precision. Around 80 times slower between the 256-bit high precision compared with standard double precision. However, only 32% of slower between the double precision and the single precision. So this larger performance gap gives us more opportunity to balance the performance and the accuracy. The second question is like, what's the candidate precision? We use a composite precision library called Canterbury. It can provide definitely a better performance over the arbitrary precision, and also it can have enough accuracy compared with standard precision. And also it supports both CPU and GPUs. Last, it also supports a variety of bit representations. Specifically, users can specify this n using Canterbury library, indicates how many double variables used to represent a single variable. For example, 4 double variables can represent a 256 high precision per variable. Okay, knowing this, let's look at some other tuning choices we made for our tuner. First, we use operation-based tuning instead of variable-based tuning because we want to focus on the computational pattern analysis. For example, those repeated accumulation like global summation. Those patterns are directly related to the operation. And second, we use iteration-based tunings. So we tune a group of operations in each tuning iteration. This could help us to reduce the tuning overhead because after each tuning iteration, we run the programs to get the error rate and also the speed up. In this case, tuning a group of operations can largely help us reduce the tuning overhead. Okay, let's look at the next question will be, what's the tuning order between different operation type, like tuning addition first or tuning multiplication first? Let's look at our overall tuning design. From left to right, let's look at first, our tuner accept the C and C++ and use a client compiler and also use the can specify their error band. Then we embedded our Autotuner inside the LLVM infrastructure. So specifically, in the very first iteration, we called it a zeroth iteration. It is converting the original program into a 128-bit high-precision temporary program. Then, in subsequent iterations, it keeps tuning down groups of operations and variables from high precision to low precision into double precision. And also, you can see after each tuning iteration, our tuner will check if it reaches error bound provided by user, or it tunes the entire program to the double prime programs. And then we know our flowchart of our tuning. Then the question will be, what's the tuning orders for this iterative tunings? Let's look at our tuning strategy line. As we mentioned, the first consideration will definitely is the loops, because like those repeated accumulation patterns have a huge impact on both performance, especially the accuracy. And also this error propagation will be more severe for those variables in the loops because they executed much more frequent than those variables or computations outside loop. The second, we actually found there are some computational patterns that will be similar to those repeated accumulation like global summation. So we define the sequential length of the same operation type as accumulated dependencies for operation type. For example, this equation here, for the multiplication, there's no contiguous multiplications besides the single multiplication operation. So 80 is 0. However, for this, after this addition, there are two contiguous additions inside. So we define the 80 for addition here as 2. In this case, different operations would have different 80s. Then we can determine the tuning order between them. The last consideration is like the number of occurrences of operation, because MBOP. Basically, what we want to do, we're tuning all operations of the same operation type in a tuning entity in a single tuning operation. In this case, it means we want to tuning, for example, all the addition in loop 1 in this iteration, and then tuning all the multiplication in the next tuning iteration in this loop. In this case, we can largely reduce the tuning iterations as we mentioned. To correctly handle the number of occurrences of the operation type, we multiply the number of operations in this type, multiply its inclusive loop size. With those tuning strategies we introduced, let's look at how to determine the orders. So to determine the tuning orders, there are two tuning entities in our tuners. The first we call it function level, the second we call it loop level. I will focus on the loop level introduction because the function level will apply the same rules. So for loop level, we first need to determine the intra-loop tuning. Basically, it's the tuning orders between loops. We do this like tunings. First, we tune all the operations outside loops first. Then we tune those loops with fewer iterations first, because those fewer iteration means like less error propagations. In this case, we can basically have the orders for different loops in your function. Then we need to decide what's the tuning orders between operation types inside each loop. We call it intra-loop tunings. In this case, we will tune a group of operation with the same type in each loop. So the orders between those operation types in each loop is decided by the accumulated dependency first. Basically, we tune the lower AD operation first because they have less error propagation. And the second, if the AD are equals for two operation types, we use the number of operations to tune lower number of operations type first. This also have a same reason because it has less error propagation. In this case, after these tuning strategies are applied, we can have the orders for all functions and all loops and all operation types inside loops. Then the tuning plan is generated. Basically, the tuning plan consisting of the orders between functions and order between loops and orders between operation types inside each loop. Then look at the next, what's implementations. We use a compiler LVM infrastructure to implement our Autotuner. Basically, we embedded our Autotuning in the optimizers of it. Specifically, this is the implementation graph. The main work for our tuning is in the middle. We have two big tuning stages. In the first tuning, we call the tuning up. Basically, we increase the precision for our digital program to the 128 or 256 Cambry hypersync library. And then in the subsequent iterations, we will tuning down the programs from high precision to double precision based on the tuning plan we just mentioned. This tuning plan is generated by the floating point recognition, floating point profiler modules. They do the detections for floating point computation and also do profilings to construct the tuning plan. And then the floating point insert and replace module will do the accuracy maximization and the precision tuning down based on the tuning plan. Okay, after knowing this implementation design, let's look at how our tuner works in the real benchmarks. For the evaluation, basically, we run our tunings with benchmarks on an Intel Xeon CPU. Basically, we choose the 108 Cambry as high precision and also use a 256 arbitrary precision called GMP as a golden solution, and then also compare results with double and single precision. We use like two big kinds of benchmarks, one called complex code, one called simple codes. We only show complex code because they have a large amount of like computations and also like more variable inside. It's called CFD and SP from Rodinia and NASA parallel benchmark. Let's look at the first benchmark called CFD. The x is tuning iteration, y-axis on left is the average relative error, y-axis on right is the execution time. The straight figure indicates different data size and also different running configuration. The time steps here means like the running times for the computation. The first for these red lines we can see is tuning errors. We can see the mixed precision tuning error with solid lines always has better accuracy compared with double and single precision. Second, we can see these solid lines for our mixed precision. The performance improved with more operation are tuning down to the double precision. The third, we can see the trend stays the same across different input size and time steps. This can improve our robustness to the input variability. Last, we can see the mixed precision tuning results. The GMP is almost 7 times longer than the composite precisions in the iteration 0 with 128 composite precision library. And then for our mixed precision tuning, we can look at the iteration 17 here. We can achieve 1.5 speed up compared with full 128 high precision code. And also additional 6 more data accuracy compared with the pure standard double precision code. which can prove our balanced performance accuracy. And then users can choose any intermediate precision tuning results based on their own needs for performance accuracy. For SP, you can see they have the same like a balanced performance accuracy trade-off, and also the trends stay the same between small and large data set data input. And also for the mixed precision tuning, we can see for iteration 151, we can achieve 2.5 speed up compared with the full 108-bit hyper-precision code, and also 2 more digit accuracy compared with a double precision code. Okay, let's look at the third evaluation, is to compare with state-of-art mixed precision tool precision use. Let's focus on these two iterations. In the middle is an exhaustive search for those number of variables in different benchmarks. We always have way better tuning iteration. This is because we use the computational pattern with loop analysis to reduce the search space a lot. And also the tuning time here is already have all the tuning iterations, also with the program execution time. Okay, let's look at the conclusions. First, we provide robust tuning strategy for mixed precisions with floating point applications through leveraging the loop analysis that reduces search space a lot. Then we'll also offer a compiler-based tuning solution for those mixed precision tuning. And also we can say we have a very effective trade-off between accuracy and performance. In last, we also provide an opportunity to extend our work to more platforms and precision domains, like the FPGA and GPUs can also be applied similar strategy. And also we can also apply our tunings on the lower precision, like 8-bit or lower bit for those deep learning libraries. Okay, that's the presentation. Any questions? Thank you.